Hello, today we're taking a look at On the Biology of a Large Language Model, which is a sort of paper published by Anthropic on their kind of series on transformer circuits, where they investigate what's going on inside of transformer language models and sort of how do they come to their conclusions. Can we say anything about what's happening internally? Obviously, a lot of people nowadays are talking about reasoning models and things like this. But now, like, setting all of those aside, even basic language models are able to do quite remarkable things. And the question is, how does that come to be? Nobody ever programmed any of these models to do, for example, poetry or addition, or multilinguality or anything like this. And the question is, can we say anything about how that happens internally? This is, the title says, kind of a biological problem, meaning that in the past we built machine learning models and we built them in a way so that they would do something. For example, support vector machines or things like that, we understood quite well how they did what they did. However, in this new era of large language models, we don't. We simply train the thing and then capabilities emerge, if you will. And so we're much more in this realm of being a biologist and sort of poking the thing and seeing what happens, and by doing that, figuring out what happens. So Anthropic has invested resources here into looking inside of these models and trying to come up with methods to decipher what's going on. This paper, let's call it a blog post. This blog post right here goes into sort of the phenomenology of that, and does so by example. So they have quite a bunch of examples right here, and for all of these examples they're able to use a method, and we're going to see that in a bit, what that method is, called circuit tracing, in order to try to explain what's going on in terms of what features are activated inside of these models, and therefore a little bit in sort of how these models think, quote unquote, or come to their conclusions. Now, I have to say, for a lot of these examples, I'm not so on board with what Anthropic says about it, or how they frame things. They frame things very much in an pro-anthropic way, whereas I think in a lot of these cases, simply the explanation is something like fine-tuning works or something like this, but it's framed in this very, the internal circuits and the analogies and blah blah blah. But we'll go into that. There is a companion paper / blog post, however you will, that explains circuit tracing in more depth, and that is a method by which you can trace the circuitry of these models. The way it works, just briefly, because all of the examples we're going to look at are built upon circuit tracing, the way it works is you take a transformer language model and you train a replacement model. So you train a model that's supposed to mimic the transformer in a lot of ways, and we're going to look at that in quite a bit. And then you use that replacement model, which is a more interpretable model, so that as you run data through the replacement model, it gives you more interpretable sort of intermediate signals, and you can look at those in order to figure out what's going on. So these are called replacement models, and they're built using a type of model called a transcoder. And that if you replace the model with a transcoder and run data through it, then you get these things they call attribution graphs. Attribution graphs are sort of like which the output is made by which features, which individual features that exist, and these features in turn are made by which other features, and so on. It's going to be easier once we actually look into it, but just briefly, how how is this transcoder, this cross-layer transcoder built? So consider a regular transformer. We're going to focus in particular on the multi-layer perceptron features of the transformers. So the attention we're going to leave in place. We're going to look at the MLP features here. And what we're going to do is we're going to train this replacement model on the right-hand side, this cross-layer transcoder, to match the output of every single layer of the transformer. So layer by layer, we train a different model and we run the same data through it. And then the transcoder is just trained at every layer to match the output of the transformer. So meaning you could, if this works well, you could just swap out the transcoder, still use the same attention computation, right, forward propagating the signal, because the signal at each layer matches the transformer. However, the transcoder you program with sort of a couple of extra things. First of all, and that's just visually seen right here, it has a lot more nodes, if you will. They call this features. Now, in the MLP, they call it neurons. In the transcoder, they call it features. And that's more of a distinction they choose to make. But the reason they choose to make it is because the transcoder's features are supposed to be more interpretable. How come? First of all, every single layer of the transcoder, it gets all the outputs of all the previous layers. So whereas an MLP only ever gets a signal from a previous layer, so you propagate the signal from this layer to the next layer, then it's processed, you propagate it to the next layer, and so on. A transcoder, on the other hand, at layer 5, it will get the output of all of the layers before, not just like a single like the single previous layer, but all of the layers before. What does that mean? It means that if some layer 5 computation needs signal from a layer 2 computation, just because it does so, the transcoder can get it directly to that model, whereas a transformer would sort of have to propagate that through the intermediate computations. So that's one thing, is it just makes it much clearer what's coming from where, right? Obviously, if you train these models well, then the models will sort of choose to go the path of least resistance and just pass the feature directly. So it means you get a much better insight what information comes from where as you look at a particular layer. Whereas in a standard transformer, again, even if it is true that the layer 5 computation needs data from layer 2, you wouldn't notice, because it would come by means of being put through the layer 3 computation, through the layer 4 computation, and the model has to kind of learn to preserve that while also doing its other computations. So it makes it much more clear. Second, you train it with a sparsity penalty, or a sparsity regularizer, meaning that one particular feature, or it makes these features more independent. It encourages the model to not use overlapping representations. So usually in transformers, it's very hard to interpret intermediate signals because all kinds of overlapping information is put onto it. Like if you have vectors representing intermediate concepts or superpositions of concepts and so on, all of these things are happening. Whereas with the transcoder, you encourage it to use one particular dimension or one particular feature here only for like one particular thing. And if it is active, then the model is encouraged to not activate the other features. That's what a sparsity penalty does. It essentially says, try to activate as few things at a time as possible. And that means if the model can choose between propagating a superposition of things where all the things are active, it will rather choose to layer the things it wants to superposition into individual features and then deactivate the rest. I hope that kind of makes sense. That's just sort of more basic loss shaping. But as a result, we do get a model that is trained to match the output at each layer of a transformer while also being sparse. And due to its translayer properties and also some few more finer details such as which nonlinearities are used and where and in what way, we do get a rather sort of interpretable output of any data we put through it. Because of these more finer details, in addition to being sparse, feature contributions are also encouraged to be rather linear, meaning that at the end, we get a graph that essentially says, okay, this feature here is the result of this feature here plus this feature here. And these together in a rather linear fashion contribute to that feature. Now, obviously, what's the downside? Why don't we do this all the time? Why don't we just train transcoders? As far as I understand, they are computationally more burdensome to train, less stable if you wanted to train them from scratch. Like, we just train them to match the transformers. And also, you do lose performance, right? If you don't process features layer by layer and rather shortcut and encourage that, you may in turn lose. Like, every regularizer you introduce, such as matching layer by layer, such as sparsity, such as more linearity, loses you performance. And therefore, the biggest criticism you could levy here, and that's probably the crux of the paper, are what the transcoders do actually the thing that happens in the transformers, or are you simply kind of getting the same output, but the transcoder is leading you to a quite wrong conclusion about what happens? And the way that Anthropic tries to kind of battle that is with so-called intervention experiments. So just here, we have the losses. So the trans cross-layerism is used with a done with a jump ReLU. You can see that here the output of one layer is not only achieved by the last layer, but actually by the by all of the layers before. And then we have a loss to match the output at each layer and a sparsity penalty. Yeah, so you can see this, we do this across layers and just replace the original transformer model with the replacement model. And by that, we get these attribution graphs. And the attribution graphs, I'm sure they show them somewhere here. The attribution graphs are just, you see which of the features become activated, which, because the model is now sparse, should be not as many. And then what you can do is you can sort of group them together, features that are very similar or very correlated. You can group them together. Additionally, Anthropic also manually goes in and groups features together and sort of gives them names. And so they get this kind of interpretable thing. So the attribution graphs are going to look something like this. So here the prompt is the National Digital Analytics Group, and then bracket open, and then uppercase N. So this is very likely that we're going to look for the acronym of this organization right here. So the question is, what encourages the model to output DAG uppercase as the next token or tokens? And the attribution graph can give you sort of hints of that. In this case, we're looking for rather linguistic features, whereas in future examples, we're also going to see that we get more semantic, if you will, features. So the way to read these here is at the bottom, you have the input prompt, and then we're going to wonder, how does this next token come to be? It's important that what they do is they use the transformer to actually run the inference, and then they use the replacement model to run the same data through and explain what is happening at each of the layers. So the way to read this here is these stacked boxes here are either manually or semi-automatically aggregated features that are active at a given token. So the token digital activates a feature that they call digital. So this is Anthropic gives it a label called digital, and they interpret this feature by looking at these visualizations right here. So this feature group, you can see, are all features that are highly active whenever the word digital appears in a piece of text. So these here are the highest activations on a given reference corpus, presumably similar to the training set of the model. And you can see the highlighted portion are which tokens are activating this feature a lot. So here, relatively straightforward, whenever the word digital appears, these features seem to be activated quite a bit. You can also see for each feature the top token predictions here that would arise from these features. So yeah, so digital has obviously different meanings. So you can also see that the different features, even though they react to different words, are often already sort of separated by themselves into the different meanings of these words. This here seems to react to the uppercase digital more. And then this feature here, in turn, activates downstream features that here, that cause the model to do certain things. So whereas this feature here is activated for the token itself, whenever digital appears, that feature is like lights up. We have to say, okay, how does the model actually decide on the next token? And deciding on the next token is very often done, as far as these attribution graph goes, by activating features that causes the model to output something else. So whereas here, this feature is simply saying the model internally recognizes the word digital is, being in the context, the feature say dag is simply a feature that is activated whenever the model is whenever the letters DAG are the next output. So you can see the types of reference data activations here. It's all this feature is extremely active whenever the next output is DAG, and you can see the top token prediction is also DAG. So there appear to be what they call input features, which is just kind of like features that react to things being present in the input. And there appear to be output features, which is just features that are being activated to cause the output tokens to be a certain way. And then obviously the in-between is the thinking, so to say. Now this here, there is only one, let's call it a semantic feature activated. So by means of opening a parenthesis and starting here with the letter N, that activates a feature that Anthropic calls say or continue an acronym. So what they do is they go to these features and they look at the top activations and they say, okay, this feature is very active, always on the first part of an acronym. And so it probably causes the model to continue saying an acronym. And so now you can see how this comes together. And sorry, I don't have my usual pen here and drawings. I hope that's okay. This is a very interactive blog post, so I thought we'll do it with the mouse. So now you can see the fact that, so we're pairing the fact that the word digital is in the context and the feature that says, we're about to say or continue an acronym, and that those two together are responsible for activating a feature that is causing the model to output something with an uppercase D. So all of these features are that. So the model is deliberately choosing to activate features to which would cause a D to be output. Same with an A, same with a G. And then these in turn cause other features, which cause the model to activate other things and so on. And that's how DAG is produced. So I hope that's clear how to read these. Again, the stacking itself is done by Anthropic. They are looking at the different features and they are sort of grouping them together and giving them names according to what they see in the activation and prediction analysis here. All right, so now we can dive into a couple of these examples. We're not going to dive into all of them, but I hope some of them will make it very clear what's happening. So, multi-step reasoning. Here they have the prompt is fact. The capital of the state containing Dallas is, and the correct output is Austin. So the point here is, in order to solve this, you need to first determine what the capital, like what state is containing Dallas. And once you know that, you need to determine what the capital of that state is. So it's not a straight up fact. It's two facts combined together that make the output. And so that's an example of multi-step reasoning. By the way, you can also look here at the detailed graph of these features and explore all of these things together. It's very interesting, but we don't want to go too much into that. So the question is, does the model internally do this sort of two-step thing where it's, oh, I first need to determine what state this is and then what the capital of this state is? Or is there some other mechanism? And the way this attribution graph is structured, you can see that we have features, we have kind of input features recognizing sort of capital, state, Dallas, and so on. The Dallas, in turn, is activating another feature that is Texas. So this feature, you can see, is both activated whenever Texas is the next token. So this would be more like a say Texas type feature, but it's also active for any Texas related things. So you can see Dallas, Fort Worth. I'm not sure if Georgetown is in Texas, but it's kind of like activated for Texas related things. Same here. Let's see if we find a feature that actually just activates on the word Texas, but maybe not. So the Dallas doesn't activate the same feature as Texas itself, but you can see that sort of an intermediary feature is triggered, or a group of features is triggered that kind of like represents Texas from a multitude of angles. So that you can say the model internally by at the token Dallas, it's sort of internally thinking of Texas, and that's mostly caused by the feature Dallas. Now, what's not so nice is that here, what's not shown is all the intermediate features of here Texas related. All the intermediate features that contribute to it, obviously, state contributes to it thinking of Texas and so on. Dallas causes it a lot to think of Texas, but you don't see this because these are heavily pruned. But just keep in mind there are always some connections from these other things always going into this as well. So from capital and state, we activate a feature called say a capital. This is a feature or a set of features that's very active before capitals are mentioned, right? And combined, the say a capital and the Texas related things feature is then activating a feature called say Austin. And that in turn is causing the output token to be Austin. Now, this seems to be quite good reasoning for, yes, in fact, the models internally do realize or recognize or in some way materialize this intermediate step of reasoning. However, what you can also see is that, for example, Dallas is causing relatively in a more direct way the feature, say, Austin, right? And Texas is causing in a more direct way the word Austin as well. So what you can see is that there appear to be an overlap. So there appears to be at least some sort of internal materialization of the intermediate fact going on, but there also seem to be quite a lot of shortcut connections where it's just like, oh, you said, oh, Texas, Austin. That's just like word association. The same thing for Dallas and say Austin, like the amount of text where just Dallas and Austin are mentioned together are enormous on the internet. And therefore, you can see that there's also a very direct path from these features. So this just alludes to the fact that, yes, probably these models do learn in some way to do this kind of reasoning, if you will, or at least internally materialize more abstract features. But then the final outcome is sort of an overlap, a mixture of all of that combined with very shortcut type features where it's just word associations going out there. And here you can see how things like hallucinations and so on come to be. That is whenever these two things are in conflict. So whenever the statistical word associations and so on are in conflict with the reasoning approaches, and when they go the same way, you get this right here, where that's a pretty clear, all the features point in the same way, but when they point in different ways, that's where you get the problem. So if the model is supposed to output something that is unlikely given the more surface level statistical associations between the tokens or between the phrases. They do these intervention experiments, and this is kind of their biggest claims to why their transcoder replacement model is valid. That's because they say, well, if it is valid, what we can do is we can actually kind of suppress certain features from propagating or even invert their signal. And then the outcome should be kind of interpretable. So in this case, when they suppress the, say, a capital feature, then the output is no longer Austin, it's Texas, mostly Texas. So the word Texas, not Austin anymore. If they suppress the feature for Texas, then Austin is suppressed pretty heavily, and so on. So you can see that if they suppress certain parts of this attribution graph, they can cause the output to be different. But it has its limits. But this is kind of like they say, well, if our method would be kind of crap, then these interventions shouldn't lead to the outputs that they do or to the change in outputs that they do. I don't fully agree, but for some things, it's certainly, I see that's correct. They can also put in alternative features, so they can run a different data where, for example, we're subbing Oakland here for Dallas, which causes another set of features to light up, which Anthropic calls the California features, which is kind of the analogous to the Texas features. And then they can take this signal right here and substitute Texas for the California features, and you will get kind of predictable results. So even though your original tokens are capital state, Dallas, and so on, if you substitute in at this particular point the California features, you swap the output from Austin to Sacramento. If you swap in the Georgia features, you get Atlanta, and so on. Interestingly, they can also do this with other countries or territories. However, they have to do a much higher absolute value modification. That means kind of like the concept of a place is itself a bit washy. So the concept of a state seems to be kind of the same as a concept of a country or a territory or an empire right here, but not exactly the same. So you have to do a higher modification if the thing that you're substituting in is further away from the state. So here the feature should be kind of like the state of Texas, the state of California, the state of Georgia, which is, again, a not exactly substitutable by the territory of British Columbia. Just interesting things they find, which sort of makes sense, I believe. And also means that we're still in this kind of superposition realm right here. All right, the next thing is poems. How do language models create poetry? Specifically, how do they plan out rhymes? So there's two possibilities: either pure improvisation, so they could just go and towards the end of a line sort of look for a word that is rhyming with the last line, or they could plan it out, meaning they could have, even at the beginning of a new line, they could have the end in mind and then work towards that. And what we're going to find is much more of the second than the first, which is quite interesting. So the prompt here is a rhyming couplet. He saw a carrot and had to grab it. His hunger was, and the model is going to substitute. Which one is it? One of these two: a powerful habit or like a starving rabbit. And the point is, yeah, his hunger was like a starving rabbit. That's what haiku does. So the question is, this word rabbit, at what point does the model sort of internally already have a representation of that word in place? Is it at the beginning of the line, or is it more towards the end when it's just like, oh, his hunger was like a starving, and then it's like, okay, I'm going to need some animal that rhymes with grab it. And here we see the attribution graphs. They focus on particular token positions, notably the it, which is the last word, the last token of the last line, and then the new line character. And it seems like that at the new line character, certain features are being activated. So at the new line character combined with the signal from the last word of the last line character, there's already features internally representing rhyming with it, right? Like at the new line, the model is already thinking of, I need something that rhymes with eat or it or something like that. You can see in the features here, the token here before it, so it activates things that end in like it, and then here activates things that end in that great street, and so on. So it's already representing this internally, and it even represents two specific words: rabbit or habit. You can see that these features, they either represent the word rabbit directly, or and this is what will maybe come later too, they also represent the same thing in other languages. They also represent things like bunnies. So this feature is activated at all of these different things. So it means that not only does it activate the word rabbit, but also the concept of rabbit. And that's important because if it has the concept of rabbit in mind, then it can much better plan out semantically a sentence that works towards saying rabbit. Right? The same goes for habit. So at the point where the new line is made, it kind of, first of all, it realizes it needs to rhyme. Second of all, it already internally represents rhyming with the phonetics of the last line. And lastly, it already internally has a choice of, or a features that represent a discrete choice of potential rhymes for the next line. And those features are then used in order to, when the next token is produced, in order to produce, like when the next token at this line is produced, in order to produce that. I find that quite cool and quite remarkable. Not eternally surprising, but I do think it's quite cool. Intervention experiments also, you can look at them, but at this, like when you leave the rhyming feature, but you just suppress the features for rabbit and habit at the new line token, it turns out that the biggest completion tokens for the last word here are things like crabbit, rat, savage, and bandit. So things that do actually rhyme, you just kind of prohibit it to output these particular words that it had in mind. If you substitute in other things for the words that it had in mind, then obviously you can steer it towards different things. And if you suppress the rhyming or replace the rhyming feature, then it will consequently do something else. Like his hunger was like a starving, and then you simply suppress this feature that says you should rhyme, which in turn puts less signal on these words it has in mind. So now it just goes like a language model is like, oh, as a starving hunger, like a starving something. Okay, jaguar, dragon, cobra. Again, quite interesting. And as far as the attribution graphs go, certainly the interventions do make sense. And I do believe that this gives an indication of what's going on internally here. Interestingly, they do find that things like new line tokens, but also in other places like end of sentence tokens and so on, have a big influence on these kind of planning things. So while sentences are being created, the models just seem to be kind of language modeling. But then at the end of sentences or at the end of lines, that's when the sort of planning and thinking, if you will, happens. And I believe the reason for it is quite evident, because at that point you're not constrained, but you're not so constrained by language and by grammar and by syntax and by having to continue a particular piece of text as during a sentence. So at the end of a sentence, you kind of have the maximum freedom to do whatever, and therefore you can afford to put all of your considerations on sort of the more overall planning of the text and not the minutia of keeping grammar right now, which is, I think, an informative thing to potentially build more powerful language models. And it's kind of like a hack that people, the hack of like chain of thought and something like this is just making this more explicit, right? Like giving the model the freedom to actually sort of plan out things without having to adhere to the grammar of the things it's producing right now, sort of separating those two out. So they also look at intermediate words, like, so they looked at the end here, rabbit, but you can also think like, okay, when it actually has to produce any word during this line, is it also influenced by this word that it has in mind? And the attribution graph clearly says yes. So if here his hunger was, and then a new word is like the word like is being produced, the attribution graph clearly shows that both the explicit representation of rabbit plus the sort of grammatical features, both that represent obviously the grammar structure right now, but also a feature that says we're approaching the end of a rhyming line, are active. So this word that it has in mind for poetry clearly represents, how should I say, clearly is clearly in mind of the model. It's hard to not to anthropomorphize as you go through these things. Keep in mind those are statistical models, and when we say it thinks of something internally, what we mean is simply that the combination of tokens that go beforehand activate certain features internally that cause the output distribution to shift. And all we're saying is essentially that by having a rhyming prompt, then internally that causes features to be activated very early on. At the moment it's clear what to rhyme with. It causes features to be activated to already have candidate words, already push their probability up. And so everything else that happens then is influenced by these features. And yeah, that in human terms, you would say you have the end in mind and work towards it rather than just going about it and then at the end of, when you need to rhyme, coming up with something that fits right then and there. So it's an example of planning, if you will. Also here, the intervention experiments. I invite you to look at them. But yeah, multilingual circuits are very interesting. So they wonder, how does the model work multilingually? Large language models tend to be quite proficient in translation, in multilingual analysis, and so on. And so the question is, how does it look inside? Does the model think, like, are the thinking circuits specific to a particular languages, and there's just some bridges between languages? Or is it more like that the internal circuitry is kind of language agnostic, so that, I don't know, a horse in any language kind of activates the same things? And they investigate this right here. So the 3 prompts we're going to look at is the opposite of small is, and then le contraire de petit est, and don't shout the something should da. So they all mean the same thing, and the haiku completes the 3 prompts with correct things. So we're going to look at how does this look. And it turns out, and you can investigate these yourself if you want, it turns out that fairly quickly in the intermediate stages, you see these features, these multilingual features emerge. So there will be features that are language specific. For example, the word opposite in English and opposite in Chinese activate different features. I'm not sure if I can even hover. I can't. Well, they forgot this box here. So these are language specific, but then very quickly you see language agnostic features arising. And you can see right here, so the concept of an antonym being activated, and the concept of an antonym being activated similarly by words like antithesis and antithesis, words like Gegensatz, which is the German word right here, but also opposition to, I don't know too many more languages. Contrarium, which I guess, I don't know, is Latin. But in all kinds of languages similarly activate these features. Gegengesetzt, Gegensatz, and so on. It's probably also a property of the corpus. What exactly is these top activations are. But you can see both features that are activated when the words opposite and antonym and antithesis are uttered, and also features that are sort of represent the concept or the really light up in a lot of antonym type situations. And again, these are largely multilingual. I'm trying to find something else here than just French and German and English. But I hope you can see that these in turn activate a feature called say large. So the multilingual feature for antonym and the multilingual feature representing the word small both give rise to a multilingual feature called say large, like that causes the model to say large in whatever language. And you can see the top predictions right here are large, da, big, große, and so on. And that then is then back combined with a language indicator features that then causes the model to output the correct language. So what we can see is that intermediately there seems to be at least some sort of an abstraction cross languages, and then the output language is then influenced by individual linguistic features again. So say large, da, big, okay. Where do we have continue in Chinese after opening quotes? So that's simply a feature that quote, open quote in Mandarin, which is, I don't know how you open a Mandarin quote, but there seems to be features specifically representing the language of Mandarin and specifically lighting up whenever you open a quote in a Mandarin sentence. And that will, to me, this is more probably like a superposition of a feature that represents a quote and a feature that represents the Mandarin language, but it could be that just the model learned this as one feature. And it's, that will then influence the actual language being output. So what they find here by also going through these substitution experiments, which do get interesting. So they think of themselves, okay, at what point do we actually have a crossover between swapping antonyms for synonym features and so on in different languages? And the conclusion of all of this, at least to them, is there seems to be a sort of an internal like bias towards English. And that could be because most of the training data is usually English, so that you can say kind of internally there is a bit of a mix between language agnostic and largely English thinking, and then there seem to be language specific features that just kind of influence the input and output to these multilingual circuitries. Yeah, again, you can see that the English graphs of substituting, like how strong do they have to make the intervention to achieve a particular goal? The English graphs always look quite different in terms of magnitude from the others. Also here, editing the output language. You can see that the intervention strength to change the output language to something else than English, it has to be a lot larger than changing something from another language. So although the French here is also pretty drastic. So yeah, again, these are the multilingual features. Now, what I find the last interesting experiments they do here is they do these intersection over union features. So they say we collect feature activations on a dataset of paragraphs of diverse range of topics with Claude-generated translations in French and Chinese. For each paragraph and its translations, we record the set of features which activate anywhere in the context. For each paragraph, pair of language, and model layer, we compute the intersection divided by the union to measure the degree of overlap. As a baseline, we compare this with the same intersection over union measurement of unrelated paragraphs with the same language pairing. So what this means is here they compare English and Chinese. They take a lot of sentences that are translated to both languages, and they run each of the sentences through the model, and they see which features are activated. Now, what we're interested in is what's the proportion of features that are where that both the translations activate together, and compared to the proportion of features that they activate separately. So essentially meaning how many of the features activated are kind of these multilingual features, these abstract features, versus how many are more single language features. And what's interesting is that you can see clearly that there is this hump in the middle right here. So the hump in the middle represents the layer, the middle represents the layer depth, meaning that most overlap actually occurs in the middle layers, which again concurs with our observation from before that there appear to be input features, more linguistic. Then in the middle, there is more the abstract thinking, reasoning, whatever you want to call it, features. And at the end, you again have features that are more language specific. So it's like input, then the processing seems to be more abstract. And then at the end, the output seems to be again more specific to language, to linguistics, and so on. I would concur the same graph holds in other contexts as well, maybe not as easily measurable, but I do recall a lot of papers about, BERT-like models that have the same conclusion, that essentially say the bulk of the kind of upper level processing happens in the middle section of the model, which also does make sense. Now here they do also claim that the larger model, you can see here, generalizes better than the smaller models because it has a higher degree of overlap over a higher degree of multilingual overlap. I don't necessarily agree with that, because you also have to consider that the smaller model is necessarily weaker, and therefore it's not really an apples to apples comparison right here. So it could just be that the generality is exactly the same, but because the smaller model is a weaker model, it simply doesn't manage to activate the correct features. But if you look at which features it activates, they would actually be multilingual features. So I'm not sure you can make that conclusion from these graphs. They do, but yeah, I wouldn't necessarily say that. On the terms, do models think in English? They say, okay, there's sort of conflicting evidence. It seems to us the Claude 3.5 Haiku is using genuinely multilingual features, especially in the middle layers. However, there are important mechanistic ways in which English is privileged. For example, multilingual features have more significant direct weights to corresponding English output nodes, with non-English outputs being more strongly mediated by say X in language Y features. Moreover, English quote features seem to engage in double inhibitory effect, where they suppress features which themselves suppress large in English, that's relating to their prompt, but promote large in other languages. Yeah, this paints a picture of a multilingual representation in which English is the default output. So there you have it. Okay, I think there is a lot more to this paper, including like addition, which is really interesting, but I don't want to make this video too long. So I suggest we take a break here. We return next time. I'll try to do that as fast as possible. And yeah, this paper we've discussed in our Saturday paper discussions on Discord every Saturday, almost every Saturday in the evening times of Europe. Happy to have you join, and see you next time. Bye-bye.